Hi, I am Ben Sepanski, the CSO at Veridise, and with us here today is Tamir, the head of cryptography at Succinct, to tell us a little bit about SP1, what it is, and what's coming up next.
Yeah, great to be here.
All right. Well, I guess we can just start with the easy question of what is SP1? How does it fit into Succinct's broader mission and, what you guys have been working on lately?
Yeah, so Succinct is a company that is doing verifiable compute. And mostly we've been focused on zero-knowledge proofs, which are a way to verify that some computation has been done correctly without redoing the whole computation. Even the name Succinct come from like the succinctness property of these proofs, which means like verifying the proof is much less work than like doing the work, which is very useful when the work is really big. In the context of blockchains, it's really helpful for scaling blockchains because all the nodes of a blockchain need to re-execute the entire state transition function. And if we can prove that instead of one time, instead of like re-executing, then that's a really major gain. And SP1 is really the tool that we chose to like do all these endeavors in. We started as a bespoke circuit company, so we would write circuits for. First, it was an Ethereum bridge, just a bridge from EVM chains to each other. And now it's making every rollup a ZK rollup. And in that process, we realized that DevX of writing circuits is just like not sustainable. We had to re-implement all of Tendermint in the circuit and Plonky 2-based circuit. That was really hard. So we decided, okay, we need something more general purpose and like, we need to do something different. And we decided to build SP1 because for the trade-offs that we had, there was nothing that offered the same thing at the time. We had a really strong opinion about having a precompile-centric approach, or like if I have a computation that I know how to do in a circuit, I can plug that in. But the rest of the logic, I can just import a program and just run it and compile it, and it works. So that's the magic of like the ZK-VM or the magic of SP1.
So you mentioned you guys started doing specialized circuits and now SP1 is more generic. Could you tell a bit more about how the ZK-VM is separate and more general than kind of a regular ZK circuit that people used to build?
So a ZK-VM is actually a circuit. It's just a circuit that is an emulator for an instruction set. So modern, or any computer really, works by executing instructions out of a list of an instruction set. It could be ARM or x86. When we use RISC, which is this like a modern open source instruction set, and a lot of languages support compilation to RISC, so you can just like take your program, compile it to RISC-V, and our circuit is just an interpreter of this RISC-V program. And that just enables proving every program.
And you guys have been doing a lot of work recently. So you just released Hypercube, and that I think was the first ZK-VM in the EthProofs challenge to get real-time proving. Is that right?
Hypercube right now is not on mainnet yet. It will be soon. We've shown in May that it is capable of doing real-time proving. This was really the first time that real-time proving was even considered like possible. When we proved I think it was over 90%, but I think it was 93% of a big sample of blocks under 12 seconds with a lot of GPUs back at the time. And since then, there's been a lot of work in the ecosystem, including with us, of like reducing resources. And today we can do even better. We can basically prove 99.7% of blocks with like just 16 GPUs.
Wow.
So that's like a major jump in like ability, and this is like kind of aligns with the Ethereum's goals of like scaling the L1.
Mm-hmm. A lot of design must have gone in that to make the proving scale like that. We'd seen you made some switches like moving in multilinear polynomials, a new polynomial commitment scheme. What do you see as sort of the core design decisions that helped you guys get to where you are now from prior iterations?
So SP1 Turbo, which is the previous iteration of SP1, was kind of similar to a lot of other ZK-VMs. I mean, it was also very early in the game, but it's based on univariate polynomials, and kind of every instruction has its own like polynomial. And it kind of creates a problem because the verifier has to then like verify each of these instruction traces, which creates a lot of like weird tension between how you arithmetize these instructions and your recursion costs. Now, why do I even have recursion costs? Like a big program can't just be proven in one go, because the circuit will just be too big, like you will run out of memory, it will be too long, like asymptotics are going to be horrible. So normally you would split up a proof to segments. So let's say it could be temporal or it could be like functional. It doesn't have to be temporal, but it's most convenient. Like let's say here's a segment of everything that happened between clock cycle 0 to clock cycle 4 million, and then move on. And then you have a bunch of these proofs and you have to aggregate them. And you do that via recursion. And the cost of recursion is a really big thing, especially when you are talking about latency, because when you have latency, recursion introduces this like serial step where like you have to finish this layer before you do this layer, before you go on, before you reduce to one proof. So to reduce the latency of recursion, we really wanted something different. So we wanted freedom for the arithmetization of the VM. And we didn't really know how to do it in univariate. We kind of tried all these ideas. And back then, Ron, which is was a great cryptographer, Ron Rothblum, joined Succinct. And he kind of like showed us the beauty of multilinears. And we also already knew about the literature that was like all about multilinear at the time, and still kind of is. A lot of the new stuff is about multilinear. And the beauty of multilinear polynomials is they have a lot of structure. So you can kind of like do a lot of things for free. And what does it mean for free? It means like you can kind of like permute your polynomials in a certain way, and the verifier doesn't need to, you don't have to convince the verifier in any way. The verifier can kind of like compute this for themselves. And that's the magic of like the multilinear polynomial. And our work, especially the Jagged PCS, achieves that with like minimal overhead.
Yeah. So when you're iterating on the performance challenges with the ZK-VM, you've got both kind of the backend that you guys are working on. You've talked about, switching out the polynomial commitment scheme. And then you also have things that are, I don't know if front end is really the right term, but maybe the arithmetization, right? Where you have the constraints themselves and then the precompiles as well. So it's kind of a huge design space. How do you see the interplay between, when to focus on the back end, when to focus on the constraints? How do you guys approach that?
Yeah, I mean, I think that's a great question, because that's actually the reason why we went to the PCS we went, because we really don't want the arithmetization layer to be limited. Basically, what is this arithmetization layer? It's how you encode the semantics of this instruction set into a circuit. And if you can do a lot of optimizations, for example, you could have, if you're adding, this is a really simple example. Like let's say you need to prove additions of U32, of U64, U32 integers. And one of the integers is 0. Actually, adding 0 happens a lot, because the compiler will just emit this instruction to just like move stuff around or whatever, or like have a constant added to something. So if you already know you have a bunch of these cycles that are add 0, you can make them much cheaper to prove. So you can just have two circuits, for one just to add zeros, one to just add the generic thing. And the question is, can you afford to have both and have 0 overhead in recursion? Because I will call it core. For the core circuit, which is the emulator circuit, I want to have maximal freedom, because then the name of the game would be to minimize the trace area. Like how big is the circuit that I need to prove? And I want maximal freedom for that. And in order to get that maximal freedom, we kind of like, the PCS needs to work for the arithmetization. The backend needs to work for the front end, right, and not vice versa. That's kind of like the challenge we faced with like SP1 Turbo, like thinking, where does it go from here? Like, yeah, I can improve the GPU code maybe, I can improve the arithmetization, but I'm kind of blocked by this recursion cost. Like if I do this change in my core circuit, the recursion will increase. And like, I don't like that. I don't like that tension. So we wanted to break that tension. And the jagged PCS kind of breaks that tension completely, which is nice.
Yeah, that must be really freeing to just have to worry about one thing at a time.
Yeah.
With all the design components, you know, obviously these are new technologies, well, new-ish, new in production at least.
Yeah.
And, you know, highly complex, lots of different execution environments. And, you know, coming from a security company, the first thing I think about is, you know, what can go wrong? What type of attack surfaces do you guys worry about? You know, what keeps you up at night with security in SP1? And I guess, how do you guys approach mitigating those risks?
Yeah, so I think this is a good point that like it is a really complicated system. It's not, you know, cryptographic code has been audited even when it's a simple signature verification, which is not considered simple by the people implementing it, right? Because there's a lot of things to think about, like all kinds of like attacks. So, you know, a zero knowledge VM, like something like a ZK-VM is actually a really complicated system. Like you say, there's the arithmetization, there's the backend. These things are separate, luckily, so you can kind of like think about each of them separately. Usually the PCS part is more about implementing the correct protocol, like following the spec. You have a theorem, you have a paper that is pretty rigorous, and you have to follow that spec. That's usually the kick there. But in the front end, yes, there's a lot of like, if your circuit is missing its check, then nothing's stopping you from like having a false proof. So like this is really like the main thing we were worried about in terms of security. Now, what do you do about it? There's audits, which we did for the first version of SP1 and most versions after that. Very extensive audits, audit competitions, bug bounties, all that kind of stuff. But really, like the ideal is to have some mathematical guarantee. In which case there's like a formal verification effort that has been going quite well. A lot of the work we did with Veridise was around verifying that the circuit is not under constrained, namely that I haven't forgotten to say that this variable needs to be something. And if I didn't say that, you know, the tool Picus will catch that and complain. So, you know, having that check run on all of our circuits is already a major win. And it's also a good thing to like catch bugs early on in development. But even going one step further than this under constraint bug, we were really interested in verifying the semantics of those constraints. So we really invested in formal verification using interactive theorem provers, in this case Lean. So we hired some domain experts in this, and also hired, also like worked with Nethermind Security and the Ethereum Foundation to really like verify that the constraints that we've spec'd out match the RISC-V semantics. And there's an official RISC-V spec in Lean. So we're able to link that to our so there's a RISC-V spec of like, what are these instructions even doing? Then there is, given these instructions, what should the circuit be constraining? Right. That's one theorem. Then there's another theorem. If the circuit is constraining these things, then the semantics is being fulfilled. So like this bidirectionality is really important.
Yeah, that sounds like a lot of work. How have you found it different working with kind of the interactive theorem provers and the SMT-solver backed approaches, kind of like Picus?
Yeah, I think Picus is much more, you can do your own. It's like a tool that I can use. Like if I can just like annotate my code. Basically, the only thing Picus needs is to know if something is like on purpose, doesn't need to be deterministic. If it's like a constraint that's like, oh, I know that this entry is just like the inverse of something, and I just use that to prove that something is not zero. So other than these small annotations, Picus is just like automatically will like scan all the error space, and if there is an error, we'll find it eventually. If it doesn't finish, sometimes you need to like okay, let's do this part and then this part. But it's pretty nice to use in general. So that's something that's like even like our team can just do. Whereas like the theorem prover thing really requires domain expertise and a lot of effort. And I actually didn't believe we would be able to do that so quick. Like it was a few months and I thought this will take like way more. So yeah, but it's really thanks to like the expertise of like our team and Nethermind. So
as you guys integrate more tools into the ZK system, has you found that it affects how you design and like the rate at which you iterate? And I guess I'll keep throwing multiple questions at you, but are there other tools that you kind of wish were present that, you know, are not available to you guys now?
Well, I think the development of these circuits is still quite manual, and like there's not much like error handling, if like, or you know, it's not like writing normal code or like the type checker is almost always gonna help you with all the dumb stuff you do. Yeah, there's probably, I think I want to desire to a more semantic way to like introduce the constraint. If I have a more semantic way to even specify the constraints, then I'm guessing I will also have a better way to like emit them. So for example, one thing that I would want is maybe if I have a better way to specify the constraints, then I could translate them to like a verification language to see that they're correct, and it's much easier. And then I can also translate them to like, I have a bunch of optimizations maybe I want to do, but I don't want to verify the optimized version. I want to verify the like easier version. So that's kind of thing like basically a compiler infrastructure doesn't exist for these things, or exists. Okay, it's not true that it doesn't exist. It exists somewhat, but we haven't like fully used something like completely modern. So yeah, I'm excited to see what.
Yeah, that's great to hear, because we're working like actively. I don't know if you know of LLCK project, which is kind of an intermediate representation that we're working to make sure is both analyzable for like Picus, so it can analyze those things, but also makes it very easy to express. So I'm sure we'll talk to you guys at some point.
Yeah, I think
about these.
I heard of it at some point, but it wasn't. I will have to explore more, because that sounds like really something that's missing for us, at least. It's like right now we're verifying the optimized thing that we already did, and so it's kind of like going like this.
Yeah, exactly. Not kind of a middle layer to let those optimizations happen by a machine.
Yeah, and then actually all of modern software works like this, right? Like you write some code that you do some optimizations in this intermediate level, and then it goes down to like another level, and you do more optimizations there. And
yeah. So one thing I want to circle back to again is the precompiles aspect. So you mentioned, you know, Succinct takes a very precompile forward approach to ZK-VMs. And now you have a lot of freedom with Hypercube to kind of throw in precompiles when you need them. How do you go about deciding when to add in a precompile? And I guess, does that affect for you any of the thoughts on the security of the system at large, or is that something you can easily throw in?
yeah, so every precompile is basically like writing a new circuit, which requires all the verification and efforts, like running Picus on it. Maybe formally, by the way, formally verifying it is still a little difficult for the precompiles because they're really, really big. Something like Ketchak is kind of a lot still for these tools. But if we could formally verify them, that would be great. But yeah, audits and doing all the security like due diligence on every precompile is really like the most of the work. Then there's the other part you alluded to, which is like, does the proof system pays for it? And Hypercube currently in its current form pays a little bit, about like the verifier still needs to know what constraints you're doing. But we actually have some work in progress to like eliminate everything. So like the verifier doesn't need to know the constraint, needs to know like a digest of the constraint.
Oh, cool.
And then just like send whatever you want. And then maybe people can write their own verifications. Where I think I'm most excited to integrate this is like, speaking of compiler infrastructure, there's been a lot of development in like automating this precompile process. So instead of writing hand circuits for every like computation you see, maybe you just like automatically know that this block of code can be just translated into a more efficient representation. So you just do it automatically, and you can formally verify the process of doing that, perhaps.
Yeah, that's almost kind of an interesting dual to the ZK-VM concept, right? Of like, instead of taking a program and emulating it inside of a fixed circuit, you take a program and generate a fixed circuit that like implements it directly. It's
Yeah, it's kind of circumventing back to the circuit, but like that's what you want. Like the circuits have less overhead. So if I can make the developer, the ZK-VM exists not to be a ZK-VM, right? Like I don't need to prove that every RISC cycle was executed correctly. I need to prove that this program does what it promised to do. So if the user still compiles a normal Rust or C++ or whatever program, and the VM just does it in a safe, fast way, then like that's what I want.
Yeah. So we talked a lot about security of, the arithmetization, the circuits. We mentioned, some of the backend. But there's also a whole other side to ZK-VMs, which is the prover, the dreaded performance barrier, but also comes with its own risks as well, especially when you start talking about things like privacy. How do you guys think about what the prover should, guarantee to people, where the prover should run? I guess, what are your high-level thoughts there?
Yeah, so actually, we started going into privacy in a very trusted mode. So we have a service of succinct private proving, in which you send your inputs to a prover running in a TEE, and kind of like there's opening a channel between the TEE and the user encrypts and sends things to the TEE. The proving happens there. We have our Grout16 wrapping layer, so like it actually is a zero-knowledge proof in the end. So from the proof, nobody can read your inputs. Where's the risk? Obviously, if the TEE gets compromised, there's a risk. We use, some cloud provider, and that's kind of something known to users, that like this is the amount of privacy that you are getting. Usually for a lot of these inputs, it's okay. It depends on the customer. Some customers are like, okay, I'll send it to this TEE. Some customers, like institutions, are more like, but if I run it in my servers, it's okay. So, okay, if they have servers they can run, that's also fine. I think really in the future, we will try to see more and more of this amalgamation of like client side, server side, what happens where. What kind of data would you send to a TEE? What kind of data would you not send to a TEE? Like right now, I'm uploading my driver's license in 500 websites, and I don't like that. Would I send my driver's license to a prover to get one proof that just works? Like, yeah. And if it leaks, okay, that is a problem, but it currently is lying in all these databases that can leak. There's also a difference in like managing data, right? If a prover doesn't need to keep your data, it's just ingesting it for a proof and can delete it after, then there's this like nice guarantees of it's easy to not lose your data because I don't need to keep it even. So that, I think there's a lot to like think through there. Obviously, not everything can be sent server side, and client side proving is really important. So I think we'll see a dependence on how complicated the computation is, how sensitive the data is. There's kind of like this trade-off.
Definitely. Do you see, because I know some approaches take sort of an incremental proofing strategy where maybe a small proof is done locally and then a larger proof that is given sort of only an intermediate proof will actually take that and do something with it that requires more server-side computation, but this is obviously kind of hard to express. Do you see that as a avenue you guys might go down that might work its way into the application layer?
I think it's early to know. I think there's definitely a possibility. Again, it really depends on like how sensitive is the data, what does that mean to send something to a prover? What can the prover do? There's all these kind of ideas of like, is the proof contain some like nullifier that's like it's one time. Even if the prover makes something, it cannot like steal my ID data forever. Or like, it depends what kind of data, what kind of sensitive things. I wouldn't send something too sensitive, right? Like, but things that I currently, I want the future where at least the things I currently upload to places are not being kept anywhere. That's like already a good, a better future in my mind. And as kind of like proving progresses and like things get more and more like device side, like that's already better. Like that's the idea. For example, the recent work by Google, for this age verification circuit, like definitely a great circuit you can do.
Yeah.
The question is what happens when it's like something more complicated that like your phone might do in 20 minutes instead of 1 second. Like, so that's kind of like where I'm, kind of these use cases are, I really like things that are interesting to me, like what kind of computation people want to prove and like who's going to do it and what guarantees are the users going to get. Like that, I think that's kind of an exciting field.
Definitely. So I guess the last kind of general security related place I'll stick is just on the cryptography side, right? So parts of ZK are still developing, new systems are coming out, obviously, new results are going on, right? There's been lots of discussions of proximity gaps in the last week, and everybody has to carefully decide where they want to position themselves theoretically. How do you guys go about deciding sort of which cryptographic threats are the most concerning, and how much of an emphasis do you guys take on making sure things are completely provable versus working with conjectures or other types of like new and very cutting edge systems?
Yeah, so I think Stark or Stark-based systems a lot of them have been using these conjectures until this day. And I think in general, it's been kind of training wheel for the field. Like, okay, we wanted to get performance. We're willing to rely on these conjectures. They seem kind of plausible. In SP1, for example, so what are these conjectures affecting? They're like conjectures about when you prove something about polynomials, it's just like you're sending some random evaluation of it and you want to prove that this random evaluation actually came from a polynomial. So there's all these questions of like, given all these random values, how close is a polynomial to those? So that's why it's called like that's the proximity is from. And what changes in these proximity gap conjectures is a parameter. So it's from a sliding scale where like you can have your security analysis rely on the conjectures, and if the analysis relies on them, your parameter would be better for you, meaning the prover does less work with the same security. Recently, based on all the new developments and also just in general, actually, since the field have been maturing more, we've been thinking about it independently, but the recent works by, Grun and Diamond and others have shown that like these conjectures are actually false as stated, and they, push the envelope a bit more. Actually, in SP1 Turbo, we kind of took a little bit of a slack. We're like, okay, the full conjectures allow me to do 80 queries, which is like this parameter that I'm using. I'm gonna do 100 to just like be within range, like even if the conjecture breaks a little bit, like that's still fine, which is kind of what happened. We didn't have to change anything.
Okay.
But for Hypercube, I actually think since it's like so much better, so much more performant, I think we can just like let go of it and instead of relying on conjectures, rely on the provable results and then let the literature like make it better. Okay, if they prove something better, I will use it. And already there's like interesting work by Ben Sepanski and others and Ulrich.
Yeah, absolutely. I know you guys also have, lots of cryptography work you guys do at Succinct. I know like Ron Rothblum, for example, has done some exciting work on Fiat Shamir there. Do you guys have anything, I guess, coming down the pipeline on cryptography-wise or SP1 that you guys are excited about that is kind of still in development, or are things very focused on the kind of current prover optimization?
Well, a lot of us have been really focused on optimizations. There is a line of work that I kind of mentioned earlier for SP1 to currently the verifier needs to know how the constraints look like. We have a line of work that kind of like upgrades on Jagged to like eliminate that. And Ron has been doing a lot of interesting work on like pushing the limits of PCSs and also on analysis of security. So for the PCS part, recently they have this work with people from Espresso, such as like Benedict Boons and others, and William Wong and Giacomo Finzi about tensor PCSs, which is like even changing the design space a little more in terms of like the trade-offs the provers can have. There's all kinds of exciting cryptography work, and then there's the Fiat-Shamir work, which was very interesting because when Ron first joined Succinct, it was to have a better connection between the theory. He's like really one of the leading theorists of the field, and the practice. Like we saw that the practice is kind of like catching on, and wanted the theory to match it. And one of the things that came up was the security of Fiat-Shamir, and he had some works from a few years ago about like some contrived setting in which Fiat-Shamir broke in. And recently, by looking at it more with the help of the co-authors, it's been proven to be more than just contrived in a really like plausible circuit under like, things that people have been considering to do. So yeah, we've been basically just pushing more research on this, like with the Ethereum Foundation funding this type of research, and us kind of like encouraging people in our team to answer these questions and look at these questions. I think it's really important. Luckily, that attack didn't affect us because it needed like a generic GKR, but again, it shows how much, especially with Fiat-Shamir, you have to be really, really careful. It's a really delicate.
Yeah, there's so much that goes into building a ZK-VM. I am always impressed with the amount of work teams like you go through. Do you, on the flip side, I guess, when you're, come home after a long day and you're evaluating your life, are you thinking about, there are lots of people building on SP1 and building fun projects. Do you have any pet projects you're kind of most excited about, or applications you think are really cool, ways people are using the ZK-VMs today?
Yeah, so I mean, I think after a long day, I just want to see. I have a newborn, not newborn anymore. He's a baby.
Well,
But
congratulations,
yeah.
belatedly.
But this is something I really like, gives me energy at work and at home. But just like family. But in terms of SP1, yeah, I think there's been a lot of interesting like uses that we don't even like know about. So first, one of the main things that we do, is OP Succinct, and like new rollups using it all the time. And recently we've been looking at like the total value secured by SP1, and it was quite insane. It was in the like billions, and like, wow, okay, like that's really cool. I mean, it's a lot of responsibility, but I think we're like trying to like do the best. We're like doing the best we can to like come to this responsibility with like honesty and like dread. And yeah, I hear people doing all kinds of random things with SP1. One fun thing I heard was Dan Bonet's lab, our class, were doing some video. They were like video attestation, and like,
Oh, cool.
seeing that videos are like edited correctly, or like,
yeah,
with
that's
SP1. It's
funny.
like,
It's a very classical ZK application
yeah.
too. That's one of the like very early knots, I think. I forget the name now, but there's a paper on like photographic editing using ZK. I don't know if you.
Yeah, I've heard of that. But it's kind of fun to see like people building all kinds of things on SP1 and in the blockchain as well. Kind of like, oh, we wanted to build even the original thing we were doing, which was bridges, and like we hear about people like modifying a client program and just compiling it to SP1 and running it. So like now they have their own bridge and they didn't even talk to us. Like, that's really cool.
Yeah, That is really neat. It comes all the way full circle.
Yeah.
You also guys have started, so you mentioned earlier that you guys had a private proving service, but now there's a whole prover network, right? What does that do? What does that enable? How has that changed using SP1?
Yeah, so before SP1 had to be used by coming to us or obviously, okay, SP1 had a prover that's you could run. Like we had CPU prover, a binary, we had a GPU. If you had a GPU, you could run a prover with our binary. But if you want cluster scale, if you want like real proof, if you want to prove a lot of things, or if you want to prove something really expensive and you don't want to run your own infrastructure, you had to just come to us or any other like person that would do it. And back then there was no incentive for someone else to do it because it's really our system. Like, what are they going to get from that? And now with the prover network, we've kind of like went all the way to decentralizing the proving. So like now you can request for proofs. You don't have to talk to us. You can just like get a proof request into the network. Someone's gonna pick it up. Usually it's not us. People have really, really good cloud operations, like are running really low prices, and it's really, really cool to see. So then they're incentivized to do it because they get rewards from the network, and users can just like plug in permissionlessly, and that's really cool. And also a lot of our customers have like, actually we've transitioned them to kind of use the network with some, with support when needed and something happens, but just like they're getting better prices, they're getting like, all the advantages of decentralization that they wanted. And some of our clients actually wanted that because they don't want Succinct to be a single point of failure in their protocol, which makes a lot of sense.
Yeah. Having that level of decentralization really makes it feel kind of part of the blockchain ecosystem, in an even deeper way. With the, EthProofs challenge ongoing, I'll take it back to here one more time. Do you guys, I guess, have any thoughts on timeline or vision of, when are we going to get down to that one GPU, 99% of the block proving? Does that feel like next Saturday?
I don't know if one GPU, but 16 we can already do, which is like a major advancement from the 160 we did in May. And there's something special about 16, by the way, which is like this Ethereum Foundation requirement to be under 10,000 watts, or like be under 10 kilowatts, because that's something that people have in their residential addresses. So if you have this like electric vehicle charger, that's like that amount of power. So you could instead prove Ethereum in real time if you want.
I mean, the perfect thing to do while your car's not
home.
home.
Perfect thing to do while your car's not home. And it's really with consumer hardware. Like you can buy these machines and prove Ethereum in real time. And that's kind of, I think, the dream of using ZK to scale the L1. I actually already see, I feel like once ZK becomes the default, or even before that, there's a lot of improvements we can do to like get the proving even faster. Even with our current prover, which has a lot of, we always know about improvements to the system and constantly doing them. So even with our current prover, we recently were contacted with the Zilkworm team that started posting on EthProofs as well. And they like made this client that is based on EVM1, but more adapted to RISC-V. So basically they looked at all these code paths that generate a lot of RISC-V cycles for no reason and kind of optimized them, and it was a 2x in performance relative to what we were using before. We're not using it yet in our real-time things because it's first for client diversity and also because it's like still in development, but they just like push the envelope so much to show that like once clients are actually gonna write programs for a prover, they could be much more performant, even from the program side. So that's like that's something that came as a surprise to me. Like I didn't expect to get so much gain for free in a way.
Right, just straight from the general like programming side, you get it. So all that open source nature, I guess really pays off when people can jump in, throw their own programs at it, do their own benchmarks. With the proving, people always talk about the 99% aspect of it, and then there's that like last 1% of blocks. What do you feel like are the main bottlenecks keeping the, I'm sure I know it's just 99% under 12 seconds, so I don't, I'm sure they're still getting proven eventually.
Yeah, I mean, actually, in terms of can the chain function? Yes, because most blocks are, even if there are a lot of gas, they're not adversarially contrived in any way. So like with 16 GPUs, you can keep up with the chain very easily. Like average proof time is like 7.2 seconds. So you can keep up with the chain.
Yeah.
And the real challenges, I think, is if you really, really want the slot time to be 12, so it has to be 100%, then we need to be able to have predictable proof costs. And right now, the gas model doesn't exactly match the proving cost the same way as it doesn't exactly match the execution cost, but like maybe that's not the main blocker for clients. They might complain about it. Oh, it's expensive. Oh, our client, it's slower than what you guys think, but it's not like a blocker to this 12-second time. With prover efficiency, maybe we can eat a lot of that discrepancy. Even now, but if you look at high gas blocks, like 35 million gas above, the proving is pretty predictable, but there's some outliers there, and they come from these like opcodes that are maybe like mispriced for proving, and already like the Ethereum Foundation, there's several EIPs I think that's going to go in to like kind of reprice those opcodes that are, some of them aren't even used that much. But also you have to consider when you want to completely shift the system, the L1 to ZK, it has to be even, you have to even consider all the adversarial examples. That's kind of the problem, not just the like average case, which is already kind of solved. It's already a solved problem in practice. The question is if someone wants to attack the chain and you have this attack vector,
right,
you have to mitigate that. So I think that's like good that they take the time to like do the work needed to figure out what this means.
Yeah. So with these adversarial blocks as kind of attack vector on the prover in terms of, I guess, in the specific context of running a blockchain.
Yeah.
You mentioned opcodes being like specific unused opcodes being the biggest source of this problem, or any standout to you that you want to call out from the EVM?
I haven't done a deep analysis. There's actually some papers that that did some more deep analysis.
That's the prover killers, I think.
Yeah, the prover killers, and I think there were the one culprit that was identified was ModX, like for RSA, and that I think is getting handled. I don't know about the rest of them. There's some things are just like more expensive, so you might be able to still, like the prover will still do it in time. It's just gonna be like closer to 12, or now they really want 10 because network latency is like closer to the time instead of like well under, which is fine. But the question is, what is the adversarial example? Like, can you get something that's like 1,000x worse
Yeah.
than the gas cost predicts?
Are there any other common computational workloads that you guys have in mind when you're building out this prover, or is right now kind of Ethereum or blockchain style workloads the main focus?
So we're trying to keep, one principle we're trying to keep with our design choices is like, is this generalizable? Like, is this general? Is this done only for this type of program, or is this like beneficial for all programs? In the selection of which precompiles to implement by hand, which we've done so far, okay, well, sketch-ack and some elliptic curve operations, like obviously is very guided by like the blockchain use case. So that's one case where it's like, okay, it is more like L1 or like even like general L2 blockchain specific. But other than that, a lot of the other changes are just in general how to prove programs better. So all those kinds of changes are still applicable. I do really don't like when there's something, sometimes there's some things you can do to like accelerate a proof of a block, because a block is like very specific and it's like between 200 and 500 million cycles usually, and it's like this type of like size. You could do things to like optimize just for that, And I think we're trying to refrain from those
Yeah.
kind of optimizations. Yeah.
That makes sense. Kind of pitching ZK as the verifiable layer of the future.
Yeah.
So keeping it as general as possible.
Yeah, and I think it will be, I mean, I think this is just the start for ZK. I think like blockchain has been, and this Ethereum scaling roadmap has been like a really great catalyst for development. And we've like benefited a lot from like the challenge, the resources, like, and all that. And I think now that the performance is so good, we'll see more and more use cases like come to life, which is really exciting.
Yeah, yeah. So I think I asked kind of a variant of this question earlier, but I know we're getting towards the end of time. Are you guys working on anything next that you're very excited about that's kind of the next step for SP1?
Yeah, so for several directions, there's some use cases we have in mind. I can't say too much, but really like this vision of we've building a company for verifiable technology and thinking really deeply about what in our world today needs verification. I think you'll come to a lot of conclusions. So like, where do we need to intervene? So there's like, blockchains is a really, really good example of a place where succinct verification is really useful. And other parts of the world are like, there's a lot of benefits to verification at all. You know, with AI getting better and better and better at like making content, like where do we go as humans to like, what do we want to live in a world where we can't tell anything that's real? Like, I don't know, like that's kind of like what we're thinking about. We're thinking about all kinds of things, but and also other than that, so we're also thinking about like other financial applications. Like, you know, there's like many people speak of ZK Hyperliquid, not something we're actively maybe doing in-house, but I think something that SP1 enables is like proving some complicated computation off-chain.
Yeah.
Like use the proof on-chain.
Bringing that type of like very heavy, crunchy finances so that we're not stuck with kind of just the most gas optimized solidity you can fit into a contract.
Exactly.
Yeah.
And also you can use it for privacy, right? Like which like wouldn't be possible otherwise. So.
Absolutely.
Yeah.
Well, thanks for taking the time to meet with us, and it's been a great chat, and looking forward to hear more about SP1 in the future.
Yeah, great being here and excited to keep working with Veridise in the future.